One of the more common things that we tend to do with descriptive statistics is to compare different groups, different conditions, different kinds of people. And it's pretty easy to show differences between those groups. But simply showing that kind of a mean difference typically is not considered enough. What I mean to say is, if they are truly different groups, then obviously they're going to be different. What we really want to know is that difference large enough to be meaningful? Does that difference actually matter? And that is something that we call effect size. So, effect size is oftentimes measured using what's called Cohen's d. This is the most widely used measure of effect size. It is defined as the difference between two means divided by the standard deviation. You can see the formula right down there. So when it comes to how you do this mathematical formula, it doesn't really matter which mean is the first one or the second one. All that really matters is that you have that difference between the means and you divide by something called their pooled within groups standard deviation. Don't worry about these technical things so much. The whole idea here is, if we want to get a measurement for exactly how big this difference is between our groups, Cohen's d is the standardized way to do that. Now, when you do the math, you're going to get Cohen's d usually somewhere below 1.0. Cohen's d is kind of similar to a z-score and how it works. It expresses the size of a difference using standard deviations. If you remember what we were talking about before, a z-score of 1 means that this score you're interested in is 1 standard deviation above the mean. And a z-score of -1 means that score is 1 standard deviation below the mean. So Cohen's d is conceptually very similar. Now, measuring this difference between means with Cohen's d has two big benefits. It makes it easy for researchers to communicate their results. You know, if everybody's using the same tools set, then they can more easily share what they found with others and be understood by others. It also makes it possible to compare results across different studies that use different measures. And we have just a few standards when it comes to determining what the value of Cohen's d means. Like, in general, if you get a Cohen's d value of about 0.8, then that means you have a large effect. If you have a Cohen's d of about 0.5 or so, then that's medium size effect. And if you get a Cohen's d somewhere around 0.2, then that's a relatively weak effect. But these are just standards. They're not, the end of the story. This is just like a common reference that we use so that we all kind of understand what Cohen's d is about. Now, here's an example of what I mean by this importance to measure the size of the difference. So this researcher, Janet Shibley Hyde, looked at the results of numerous studies on sex differences expressed in the result in terms of Cohen's d. So think back to those standards I just mentioned. A Cohen's d of 0.8, that's a strong effect, that's a large effect. 0.5 would be a medium effect, and 0.2 would be a small effect. So when we look at these differences that she found, when we look at these differences that she found, we can see that things like mathematical problem solving, we found a difference between males and females, but that difference is so small that who even cares? Like a d score of 0.08, that just means there's such a slight difference, it probably doesn't even matter. And then reading comprehension is the same story. That's a very weak effect. Smiling, though, smiling, that shows close to a medium effect. So there does seem to be an interesting gender difference in how people and how often people smile. Aggression is the same case. Attitudes towards casual sex, that's a very large effect. Wow. So that shows that there is a huge difference between men and women when it comes to attitudes towards casual sex. And then leadership effectiveness, once again, we have a very small effect. So just, you don't need to know the means and standard deviations. Just by looking at these D scores, we can tell there's some pretty big differences between men and women in some ways, but in other ways, those differences are pretty minor. So who even cares about those kinds of things? Here's one more example. Let's say you're a researcher and you're trying to determine whether your new cancer treatment that you're developing is significantly better than the stuff that's currently available. So you verified that your treatment is better, but it's only slightly better. Like you get a Cohen's d score of 0.05. What this means is that the improvement is so slight that it's quite likely that nobody will even notice. Like if you just swap the treatments and you didn't tell anybody, probably no one would ever notice. So in this case, spending time and effort to produce this treatment would be a waste of time and money. The difference is so slight that you really haven't produced anything all that much better. It's kind of, it would make more sense to move on and try to produce something that has an even greater difference, a greater Cohen's d effect size difference. So one effect size, that's just a measurement of how big these means are, really. How big the difference is between these means, I meant to say. A lot of people get confused though, because effect size kind of sounds like there's it kind of suggests that there might be a cause-effect relationship here. And I just wanted to point that out because that's definitely not the case. So I know a lot of people can be easily misled by that, and I just wanted to make it very clear. Just all effect size means is that there is a difference of a particular size between these two means. That's all effect size measures, is the size of the difference between the means. Now, Cohen's d is a great way to measure the size of the difference between two means, but there's other kinds of ways that we can describe the relationships between variables, such as correlations. Correlations are, in fact, one of the most popular ways to measure statistical relationships, but they only work for quantitative variables. We've already talked a bit about correlations, and we're going to talk more about it later on, but the whole idea here is, with a correlation, we have one variable on the x-axis, one variable on the y-axis, and we're just looking at how they move together. That's the whole point of making a scatter plot, is to see how these two variables might be related in some way. And the standardized way that we measure a correlation is something called Pearson's R. So this is a statistical value, sometimes we call it a correlation coefficient, that measures and describes the direction and strength of a linear relationship. So it's very similar to Cohen's d, and it's often also used to measure effect size. But compared to Cohen's d, it is relatively difficult to compute. The mathematical equation for Pearson's R is simply put right here, but these three different parts, the SP, the SSX, and the SSY, these three things are all individually rather complicated to compute. You could do it by hand, sure. It's just there's tons of room for error and it's very time consuming. So typically we don't compute Pearson's R by hand. But just to let you know how we do that, I'd like to mention the steps that are involved. So when it comes to computing Pearson's R, step number one is to figure out what that SP is. That's called the sum of the products of deviations. So that's step number one. And to do that, you have to first calculate the mean score, the mean value for your two variables. So variable 1 and 2, calculate the mean scores. Then you have to subtract the average value of each variable from each individual score. So you're going to get a set of different scores for each individual x value and how different it is from the mean for x, and each individual y value and how different it is from the mean for y. Then you have to multiply these two different scores together. So you multiply the different scores for x and y, and you do that for every combination of x and y. Then you add up all the products from steps 1, 2, and 3. Next, you want to determine the sum of squares for variables x and y. Divide this, yeah, you get the point. The point is, this is a bit too much. I don't want to overwhelm you. I'm not going to quiz anybody on this kind of stuff. I just wanted to let you know how complicated some of these statistical procedures are. And I hope that makes you feel a bit thankful that you'll probably never have to compute this by hand. We have modern tech like Microsoft Excel, Google Sheets, all kinds of other statistical programs that will be able to easily do this kind of stuff for you. But at the end of the day, whether you do this stuff by hand or whether you use some kind of program, you're going to get an R score, a Pearson's R score. And that score is going to be somewhere between -1 and +1. Now, the closer it is to negative or +1, the stronger it is. The closer it is to 0, the weaker it is. So here's just a few examples of what I'm trying to describe. So Pearson's R measures something we call linear relationships. So here we have stress on one axis and work hours per week on the other axis. And if your data forms a nice line like you see here, we would call that a strong relationship. When you go higher in one axis, you're also going to be going higher in the other axis. So you would expect a Pearson's R score perhaps like 0.7, 0.8, or 0.9 there. Then over here we have a couple variables, GPA and IQ. If you look at it, it also forms a line, but it's not as clear. It's not as bunched together. The dots are far more spread apart, and as a result, we wouldn't expect a Pearson's R score to be all that high, like maybe 0.5 or 6, maybe 7. And then here we have life satisfaction and monthly expenditures. You can see it doesn't really form a line like at all. If I asked you to try to draw a line to connect most of the dots, you probably really would have no idea where to put it. So that's fairly weak. And then lastly, we have autism rate and vaccination rate. And this time the dots are just all over the place. It would be impossible to try to connect these dots. So that would be an example of like a non-existent relationship. So Pearson's R does have some problems though. There are two common situations in which the value of Pearson's R can be misleading and shouldn't be used as a result. The first situation would be any relationship that is non-linear. So if you have a reason to think that the dots on your chart aren't going to fit a line, like it's more of a curve, if you have any reason to believe your dots might be in a curve shape, then you shouldn't use Pearson's R. Another reason is if one or both of the variables has a limited range in your sample. So that one's a little bit harder to explain, but just we've talked previously about things like range effects, like ceiling effects and floor effects and things like that. So if you just think those kinds of things might be a problem in your data, then you shouldn't use Pearson's R. When you do have these kinds of problems and you decide Pearson's R can't be used for you, you have an alternative option. It's called Spearman's R. So Spearman's R has a few benefits. It can work for correlations of any shape, and it can even work for non-continuous, like ordinal data. So if, for example, if you believe that your scatter plot is going to look something like these, then you should definitely use the Spearman's R, not Pearson. And one of the really cool things about Spearman's R is that the math is exactly the same. If you can do a Pearson's R, then you can do a Spearman's R. It's exactly the same math. Like, as you can see in the formula here, the only thing that's different is that we have a little s next to the R this time. So you might be wondering, if the math is exactly the same, why is it that this Spearman's R can work for, data of any shape? Well, the answer is there is one big difference, and that's before you do any math, you have to recode the variables. So before you perform a Spearman's R, you have to recode the variables so that they are now in rank order. So let me show you what I mean. Let's say this is your data. So you have 3 participants and you measure them on the x-axis, or on the x variable and the y variable, and you get those scores. To do a Spearman's R, you have to alter the data. So we want to look at x and find the lowest value and give it a 1. The next lowest value gets a 2, the next lowest value gets a 3, and so on. So that kind of data will turn into this kind of data. So if you just compare them real quick, the highest value for x was 32, so that should get the highest x value in the ordinal data, which would be a 3. So by recoding the variables in this way, it makes it possible for you to measure all kinds of things that just wouldn't be possible otherwise. Obviously, whenever you alter the data, whenever you simplify the data in any way, you are going to be losing some information, but at least by doing it this way, it makes it possible for you to do some kind of meaningful analysis with that data.